All right, hello everyone. Chapter 2, General Chemistry. Critically important chapter. This chapter is short. It's going to go by fast. But like I said before, in the room, you need to know every single detail of this chapter like you know the own front and back and side and right and left of your everything. The way that you know your environment, you need to know this chapter. The way that you know what you like to eat, you need to know this chapter. This is chapter 2, the periodic table. By the way, I have an endeavor for the November break when I go back home. Our buddy Vishal in the back. Vishal, say hi. Vishal owns the UWorld MCAT books. During my break, I will be giving them a read and giving you my thoughts. If I think that they're useful and you can stick to one resource, I will tell you whether or not they're better, worse, or on the same par as Kaplan. And that will be my endeavor for the November break, to see whether or not you guys can use those books, because from what I've heard, they're very detailed. From what I've heard, they're incredibly detailed. And if you guys can just use one resource and just, cycle it among yourselves, why not? So Vishal, many thanks to you, my friend. I want everyone, on whatever device you have, just on the side of this lecture, you can make this smaller, make it bigger, whatever it is. If you have a second monitor, whatever it is, just pull up a photo of the periodic table. Honestly, get it on your phone or get a buddy to open it up on their iPad or a laptop that you're not using, whatever it is. Pull up a photo of the periodic table. Right? The modern periodic table, the organization. The periodic table is organized into periods, which are the rows, and groups, which are the columns. And the periods represent the energy level of the row, or of the elements in it. The energy level. What do I mean by the energy level? The highest energy level. So period 1, highest energy level is 1. Period 2, highest energy level is 2. Period 3, highest energy level is 3. I don't know what's wrong with middle school. I was in middle school going to 8 classes back to back every single day. I was 13 years old. Didn't care about anything. I really just wanted to go home and watch Naruto. I don't remember any of that. I think I've repressed it. Suppressed it? Suppressed it, yeah. Repressed is of a person, right? To be repressed. I believe. I don't know, I'm not a grammarian. And the groups are a bit more insightful in the way that they work. These represent, quote unquote, families of elements which have the same number of electrons in their outer energy level. Notice how I didn't say orbital. They have the same number of electrons in their outer energy level. I love looking around the faces in this room. Some people are diligently note-taking. Some people look like they're on the verge of tears all the time. This guy is always laughing at something. Looks real good while doing it. See me after class. And my favorite row of people is them right there in the back. Those are the boys right there. They're having a great time, and you can tell. Whenever they're here, I aspire to have a friendship like that, where all you do is just go everywhere together. Even a stupid class run by some guy who has no idea what he's talking about. We're missing like the little crowd of people sitting right here, usually in the second row, making a lot of noise the whole time. It doesn't matter to me. I don't care. Oh, by the way, guys, if you haven't been to this lecture very often, I do not care about the background noise. They can't hear it, so I don't care. I'm just going to keep teaching. Okay, so the number of electrons inside of their outer energy level, these sort of outer shell, quote-unquote shell, right? We still use the word shell even though it's like energy level. These are called the what? Huh? These are called what? The valence. Valence electrons. Valence is such a nice word. It just rolls off the tongue. Valence. My materialistic ass is going Valentino. Valencia. Huh? I think that's why I was thinking about Valentino, because of your cologne earlier. By the way, guys, cologne of the day. I'm once again wearing Amouage Outlands. Oh, I have something for you. I told you I would bring you this. I think you're really going to like it, to be honest. I layer this with like everything. Try that on. It's the rose and white musk. Yeah, try that. It's really screechy in the beginning, but it'll settle down. You'll really like it.
You remind me of an influencer. That's crazy. You know the girl who does the Chuka stack of the day?
Okay.
Cologne of the day.
So the valence electrons are the electrons, and these electrons are the ones that are furthest from the nucleus. Furthest from the nucleus, right? And those, it's nice, right? Those have the, give it like 20 minutes. Those also have the highest potential energy. Because the further you are, right, the more sort of unstable that binding is between you and the electrostatic forces of the nucleus, blah, blah, whatever it is. So further you are, the greater energy you have, sort of like sitting at the top of a hill, right? Very good. So let's talk about this for a second. Periodic table sort of looks like this. Hydrogen and helium. Yeah, I can spell that from here. Wow. Hydrogen and helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium and magnesium. No? What is it? Magnesium. Aluminum, silicon, phosphorus, sulfur, chlorine, xenon, right? Argon, sorry. Argon. All right. This is all the periodic table you need to know. That's it. I would dedicate this to memory. I would. Maybe even minus this. That's what you need to know. But know that this is 3. Sorry, let me line this up a little better. Because this is important. We're gonna use this for the rest of the lecture. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Give me a second. Neon, argon, chlorine, sulfur, phosphorus, silicon, aluminum, sodium, magnesium, calcium, potassium, bromine, iodine, xenon. Okay. That is the fragment of the periodic table you need to know. And just know that the transition metals are where?
Xenon is one
Huh?
Xenon is
What's after this? Krypton?
Krypton.
Okay. We have 2, 1, 3. Transition metals are where? Here. Yes? On the way to bromine. In this bottom left corner, you have francium. Yes? And here, you have a wall. Okay, now we can start talking about this. Energy levels. Energy levels. groups. Each of these groups, group 1 has 1 valence electron. Each of these has 2 valence electrons. Each of these has 3 valence electrons, 4 valence electrons, 5 valence electrons, 6, not saying that, 8, 7. That's the number of valence electrons. Now, is that the number of the group? Not always. This is not group 7, this is group 17. Those are the valence electrons, right? You guys get that? Cool. Now I'm going to erase that and actually draw the names of the groups. Group 17 is known as the halogens. This is group 17, the halogens. That will make this group 16. The chalcogens. The chalcogens. The halogens and the chalcogens, groups 16 and 17. You guys use your periodic table, not mine. Look at your periodic table. From oxygen down is the chalcogens, fluorine down is the halogens. Hydrogen down is the alkali metals. Is hydrogen a metal? No, it breaks the rule. Beryllium down is the alkaline earth metals. And because of the similarities in their valence electrons and their ability to donate or accept electrons to the same degree as their neighbors within the same group, these atoms act the same. That smells very good. Group 17 has 7, and group 16 has 6, and group 1 has 1, and group 2 has 2. 2 what? Valence electrons. And those valence electrons will determine how they react, and because they have similar valence electrons, they react similarly. Understood?
Yes.
Yes? So the valence electrons are actually going to do what? They're going to determine the very specific. These are very specific words. Activity, reactivity, and intrinsic characteristics of the atom. So atoms of the same group have similar intrinsic characteristics. They are similar in the way that they interact with other things, interact within themselves, and exist in the environment. Do you guys understand? This is why all of the halogens exist in the world as what? Diatomic. F2, Cl2, Br2, I2. This is why the alkaline earth metals make very good metal oxides. Calcium oxide, magnesium oxide. Yes? Understood? How are we feeling? Let's read the room. Who's feeling okay? You guys good? The pace is okay? It's a bit more intense than biology, I know. We're going through a bit more information in a bit less time. Yeah, is this good? Good. Let's talk about the types of elements. That's the organization. So the periodic table is organized in order of increasing atomic number and assorted according to orbital theory, as we spoke about in the first lecture. Yes? Types of elements. Isn't that crazy? Isn't that just ridiculous? You add one atom, one tiny thing you can't even weigh or see or touch or feel or anything, completely changes what's happening. That's beyond imagination. This is not something that just happens. That's crazy. chemistry was actually a big part of the reason that I started to believe more in religion, believe it or not. Chemistry was a big part of the reason that I became more religious, and science and all these ideas, and just look at it. It's ridiculous. It's crazy. It's beautiful. Metals. Metals exist on the left of the periodic table. Not bad, right? Metals exist on the left. These are your metals. Yeah, it's talking this staircase. We'll talk about it. Metals have specific characteristics because of their identity being on the left of the periodic table and the way that they sort of interact. By the way, I just drew this. It's not like an attachment. This is the little block that you see at the bottom of your periodic table. This is the lanthanide and actinide series. We'll talk about it in a bit. Metals are known for their luster. Great fragrance by Amouage, by the way. Amouage Luster. You should look it up. Go try it out if you can. If you've got $500 to spend, it's well worth it. Malleability. What does it mean to be malleable? You can hammer it into a shape. Ductility. What does that mean? Yeah, you can stretch it into like a rod. And last but not least, they are what the book says, and I hate that they say it here, but you kind of have to, right? Where's my other marker? Where's my black marker? Oh. They are electropositive. Electropositive. They don't really attract electrons towards themselves. Things that attract electrons towards themselves are called electronegative. We'll talk about this when we talk about periodic trends. How are you feeling? Good. It's good to see you. You in the back, how are you feeling? Good. Group B elements, which you guys remember, I talked about the transition metals over here. These transition metals and everything below them are known as group B elements, transition elements you can call them. And they normally have 2 or more oxidation states. We will talk about oxidation states in a later lecture, but as a simple rule of thumb, the oxidation state is the charge of a specific atom when it gains or loses electrons to that degree. A loss of 2 electrons will give an atom a +2 oxidation state. A loss of 3 will give it +3. A gain of 2 will give it -2. Do you guys understand that? Yes? The word reduction can be believed to come from the reduction in the oxidation state. Why does reduction mean a gain of electrons? Well, a gain of electrons reduces the oxidation state from positive to negative, or 0 to negative. One more thing about metals. Have you guys ever heard that metals are conductive? They conduct electricity. This is because the valence electrons of metals are loosely held. I want to see who's very intelligent in the room. Tell me why. Nothing to do with the d orbital. What about things that don't have a d orbital? What about lithium and beryllium and sodium and magnesium?
Is it a shielding effect?
No. Wait. Hold on. Say that again.
Like the shielding?
What shielding? Shielding from what?
The metals, like in the middle especially.
Huh?
They're farther away from the
Well, what are you shielding from?
Zeth.
The Z effective, the effective nuclear charge? I like what you're saying. I just think you're saying the opposite thing. But I want you to keep going. You're kind of on the right track.
So they have a weaker effect on the electrons because of the shielding effect.
So why are those electrons loosely held?
Because there's less of an attractive force holding them to the nucleus of the
Did you guys hear that? She said that the effective nuclear charge is lesser acting on the outer electron. If you don't know what effective nuclear charge is, it's okay. Well, basically what she's saying, we will study this in the next chapter. Effective nuclear charge is very important, and I like that you said that. Now, when you go from one energy level to the next, doesn't that whole energy level get further away from the nucleus? But you're really only going from a certain number of protons to 1 plus. So you have one extra proton pulling on something that's very far away. But now that energy level is here to stay. So as you add protons, you're not adding energy levels. So as you go down the group towards the right, away from the left, you have more and more and more protons pulling on the same energy level. So it's more of an attractive force. So as you go down the group, the attractive force of the nucleus on the outer energy level gets stronger. So all the way on the left, it's the weakest. All the way on the right, it's the strongest. We will contextualize effective nuclear charge in the next lesson. I need a good 5 minutes to explain it. We just don't have that time right now. But just show of hands, if you didn't follow this time, you'll follow next time. Who followed that? Okay, not bad. Good. You're absolutely correct. Now, the reason that I said that is because since the electron, should we explain it? Should we just do it? It's 8:41. It's fair game. Yeah. Okay. Yeah, get rid of my crappy PR table. We'll draw another one later. I have an atom of neon. I have the nucleus of neon. How many protons? Huh? Neon? How many protons? 10. Neon has how many energy levels? 2. Those are electrons. 10 protons pulling on 2 energy levels, 10 electrons. And neon, because of its high number of protons, it's very tight, it's close together, right? You can imagine, have you guys ever seen those shoes where you don't lace them up, you just spin the wheel and it tightens the strings around them? Think about every proton as spinning the wheel of the nucleus and it tightens everything around it, right? Now what happens? The next element is what? What's after neon? Sodium. $11 protons. But we have a whole new energy level to deal with. That's your valence electron. Way the hell over there. And how many protons do you have extra from this to pull on that energy level? 1. Here's the thing about effective nuclear charge. The question becomes, how many electrons are inside of the one that you're talking about? So how many electrons are inside from this one? 10, just like before. And the 10 electrons here are doing what's called shielding. They're shielding the positive charge of the nucleus by 10 points. So how many positive charges does this electron actually feel? 1. Because we have 11 protons. We have to pass through the force of 10 electrons. To get to that, it only feels 1 charge. What happens when we move on to the next element? Huh? What's the next element? Magnesium. With its 12 protons and its 12 electrons. But notice what? The valence electrons are in the same energy level. When in sodium, only 1 proton, 1 effective point of nuclear charge was pulling on the outside energy level. Now how many is it? We have 12 protons, 12 electrons. How many are inside the valence 2? 10. 12 minus 10 is how many points are we pulling with? 2. Now we're pulling with, we tighten the wheel. So we pull harder. What about when we go to 13? What about when we go to 14? What about when we go to 17? 17 minus 10 is going to be 7. We have 7 protons pulling on the outer ring as opposed to 1. So as you march down the periodic table and add protons without adding energy levels, your pull on the outer energy level gets stronger and stronger and stronger. This is the reason why metals are capable of losing their electrons so easily, because their electrostatic attraction to the far away nucleus is not only distanced, but it is shielded by inner energy levels. Does that make sense? That is the idea of effective nuclear charge. Now who gets it? Does anyone still not get it? You still don't get it? Okay. Come here. You, come here. No, both of you. And you. Come here. I want you two to stand in front of me. Turn towards him. And you will do everything to stop him. Come attack me. He has to get through all these people to get to me, right? But imagine, instead of him, it was him and his brother and his dad and his other brother and this and that, and there's only these 2 guys protecting me. This is shielding. The effect of shielding decreases the more people you have on that side. The effect of shielding decreases the more people you have on this side. These electrons are trying their hardest to not be pulled in by, you guys go, to not be pulled in by this nucleus. The more and more and more people you add, the more force you have pushing through the shield. And as you push more force through the shield, you pull down on this energy level harder. So those electrons become more heavily bound to the nucleus. So as you go forward and add more protons while staying in the same period, meaning the same energy level, your effective nuclear charge goes up and your attraction on the outer valence electrons goes up, which means those outer valence electrons are held more tightly. You must understand this in order to understand ionization energy and electron affinity in the next chapter. If this didn't make sense, speak now. Ask the question, please, I beg you. If any part of this didn't make sense, ask the question. I'm going to let this hang in the air for a second.
So the center is being protected by, so the electron is they're being protected from the electron? Or?
Think of the valence electron shell as one thing. It's a bunch of electrons in one place. And the nucleus is pulling on that one place all together. You're pulling on the outer electron shell, the outer energy level. So by pulling on the outer energy level, you're pulling on all the electrons inside of it. The more protons you have with respect to that energy level, the more attraction you have. Does that make sense? Let's do this in a very simple fashion. Let's look at it in a simple way. I'm only going to draw one side of the thing. We have a nucleus with 10 protons. We have a first energy level with 2 electrons, and we have a second energy level with 8 electrons. I want you to tell me, what is the effective nuclear charge felt by these 8 electrons? 8. Why? Because we have 10, and it already went through 2 to get here. So that's 8. When we add another, we now have 11 protons. But we have filled the second energy level, right? When we add a new energy level, it's further away. So it's already looser. 1 electron. Think about p orbitals. So now when we try to pull on that 1 electron where it is, we go here. What did we pass through to get there? 10. We had 11 in the beginning. We passed through 10. It only feels the Z effective here is 1. Because it moved through 10 to get there. 10 electron charges canceled out 10 of the proton charges. Does that make sense? Let's take a look at what happens as we go up. 2. What's that felt? 2. So Z effect equals 2. What about 3 and 3? 3. Why? Because the shielding isn't changing, but the number of protons is. As the number of protons goes up, you pull harder and harder on the outside shell. I'm spending so much time on this because if you don't understand this, you're going to crash and burn next chapter. You will not understand a single thing next chapter. I'm being very serious. There's no way to contextualize ionization energy and electron affinity without this, right? Question. What's the effective nuclear charge felt by these? Second energy level. Huh? The second energy level is felt by, what do we move through? Z effective equals 11. Do you guys see you move through something, it kills your effective nuclear charge? What about when we get up to the halogens? 7 electrons, 17 protons. We're going to move through 10. The Z effective is going to be 7. It's a very high effective nuclear charge coming from 1. So that's why the halogens are very resistant to give up their electrons, being pulled in very hard by the nucleus. And this leads me to one more thing. Because of the increased effective nuclear charge, as we crank up and crank up and crank up the nuclear charge, what do you think is going to happen to the radius of that energy level? It's going to collapse and collapse and collapse and collapse, which is why as you come right on the periodic table, your atomic radius goes down. Very good. So that's metals. Let's talk about nonmetals. So we can say that metals have very high effective nuclear charge, very low effective nuclear charge, which allows their electrons to flow more freely, which increases their conductivity. Nonmetals occupy what side of the periodic table? This side right here. Yeah, buddy. Nonmetals. They are brittle. Since we explained effective nuclear charge, their effective nuclear charge is high, therefore high ionization energy. Yeah?
What is ionization energy?
Ionization energy is the energy required to rip one electron off the valence shell of the atom. We will talk about it next time. If you don't get that, that's fine. Also, so high effective nuclear charge means high ionization energy, means high electronegativity, means low atomic radius. And all this is covered in chapter 3. So if you don't understand it, you will understand it on Sunday, where we do chapter 3, 4, 5, and 6. Kidding. I'm joking. I'm totally joking. So you guys jumped out of your seats. Dang. Imagine if I did, though. And these guys are actually a lot less unified in their shared characteristics. The chemistry gets a little wacky wonky here. Willy Wonka and the Chocolate Factory.
What does EN stand for again?
Electronegativity. Metalloids are these guys in the staircase. They're known as metalloids. It's the staircase elements, but I'll list them out for you. These are boron, silicon, germanium arsenic, antimony, SB for whatever reason, tellurium, polonium, and astatine. And these are your halvesies. Kind of metals, kind of not. Kind of electronegative, kind of not. Kind of high ionization energy, kind of not. Really varied in the way that they act. These are weird. Arsenic is poison. Why? Homework. Why is arsenic poison? Huh?
Isn't Rasputin
I think he did. Yeah. I think that's the whole recipe in the story. I have an idea of why arsenic is. Yep, I know. I know why arsenic is poisonous. Funny thing is, you know how quickly you can get an answer? If you really, really think about everything that we learned today, you can look at the periodic table for 30 seconds, find arsenic, and you'll have an answer. Can anyone figure it out? If anyone can figure it out right here, no homework for the whole class. You guys do not need to find an answer to this question for me. Huh?
I'm pretty sure my biochem professor really talked about it today.
Tell me.
He messed with glycolysis.
How?
Instead of binding, basically when
Let them cook.
PFK, one of the enzymes phosphorylates to make 1,3-BPG.
Yeah.
Instead, it replaces one of those with the arsenic.
Oh man, he got it. Killed it. Everyone look at the periodic table. Everyone look at the periodic table. What is arsenic directly under? It's in the same group as phosphorus. It replaces the role of phosphates in your body. You can't effectively make energy without proper binding to phosphates. Arsenic is a phosphate poisoner. Why does it bind to the same thing as phosphates? Because it's in the same period, and I said it's in the same group. Things in the same group have the same number of valence electrons, which means that they have the same characteristics and activity and reactivity. They react with the same things. They bind to the same things. They have the same internal characteristics. Yes?
So what makes arsenic like more poisonous than anything else in that group? What makes it's like is arsenic any like more poisonous than say antimony, or is it
I don't know.
just
I guess you have homework now.
oh wow.
Thanks, man.
Look up antimony poisoning, I guess. Why doesn't nitrogen do the same thing? I don't know. Well, nitrogen can't bind oxygen the same way that phosphorus and arsenic can, right? Because nitrogen doesn't have access to the Yankees. Nitrogen doesn't have access to the d orbital. So it can't bind oxygen the same way that arsenic and phosphorus can.
Oh, it looks like antimony toxicity is like similar to arsenic, but it's just that arsenic's more available. Antimony toxicity is just as poisonous, but it's less common compared to arsenic.
Very good. And why? Because they're in the same group. It's late. I thought all the periodic trends were in chapter 3. They're in chapter 2. Guys, go home. We'll do part 2 next time. I will see you guys next time. Please check the link in the description below to support the channel, and I will see you all in the next one. Take care.